An analog to digital converter, or ADC, changes an electrical input value to a corresponding digital output value. To understand the basics of an analog to digital converter, let's define the term analog. In terms of measurement, the term analog refers to a measured value derived from the interpretation of a mechanical pointer on a calibrated scale. A typical speedometer is an example of an analog device. A calibrated scale of 0 to 100 miles per hour is used to indicate the vehicle's speed. The driver uses the information from the mechanical pointer to measure and verify the speed of the vehicle. The basic function of an analog to digital converter is to take an analog value and convert it to a corresponding digital value. The basic process is shown here. An analog value is used as the input to the ADC. The ADC produces a digital output. The 7-segment displays show the equivalent numeric value that corresponds to the analog input. Let's examine the basic operation of an ADC. The ADC shown here produces 4 decimal-weighted binary outputs. The 4 outputs can produce any decimal value from 0 to 15. The decimal-weighted output value will correspond to the input voltage value. In this example, the ADC has a voltage reference of 15 volts. In this example, the input voltage to the ADC is 9 volts, the converter produces a decimal-weighted value of 9. Analog to digital converters compare an input voltage to a set reference voltage and produces a decimal-weighted binary output. In the example shown, the voltage reference is 15 volts. Notice how the binary value is displayed for each of the voltage inputs. The number of converter outputs, the set voltage reference, and the input voltage will determine the converter output value. Let's examine the digital output of a 4-bit converter. Although the largest decimal value that can be represented with 4 weighted bits is 15, you must remember that the number 0 is a valid number. Therefore, 4 decimal weighted binary bits represent 16 values. The 4-bit table shown here identifies the 16 decimal values using 4 bits. Notice that the number 0 is included in the list. An exponent value can be used to solve for the total number of values that groups of binary bits can represent. The exponential expression, 2 to the nth power, is used to determine the maximum number of values that groups of binary bits can represent. The number 2 represents the 2 states of binary, that is often on. The exponent n is the number of binary bits. Notice that 4 binary bits can represent 16 values. Remember that the number 0 is a valid number. Shown here is a 6-bit converter and an 8-bit converter. The 6-bit converter can represent any decimal number from 0 to 63. 0 is included to make the total 64. The 8-bit converter can represent any decimal number from 0 to 255. 0 is included to make a total of 256. Let's examine how the binary value of a converter is used to determine the output resolution of an analog to digital converter. An analog to digital converter is designed to accept a range of analog voltage inputs and produce a quantified binary output. The reference voltage identifies the maximum voltage of the range of voltages. The input voltage is compared to the reference voltage and the converter produces a corresponding quantified decimal-weighted binary output. To understand the values produced by an analog to digital converter, the resolution of the converter should be identified. Resolution is the voltage unit value that causes a binary output change. Let's look at the formula used to calculate resolution and an example of how to calculate resolution. A converter produces a binary result for a range of input voltages. The voltage reference of a converter identifies the maximum voltage of that range. The voltage reference is then divided by the maximum decimal value of the converter. Notice that 1 is subtracted from the maximum number. This compensates for a binary output of 0. The result is the converter resolution. In the example shown, the voltage reference is 15 volts. The maximum decimal value of a 4-bit converter is 15. When these are divided, the result is 1. 1 volt is the resolution. This means that the binary value changes for each 1 volt increment applied to the voltage input of the converter. Analog to digital converters with smaller resolutions provide more accuracy than converters with larger resolutions. The resolution of the converter shown here is 1 volt. This is very poor resolution. This means that a binary change happens at 1 volt intervals. The resolution in this example is 1 volt. The input voltage ranges from 6 to 8 volts. Notice that the binary output changes at 7 volts and 8 volts. Since the resolution is 1 volt, the converter ignores input voltage changes that are less than 1 volt. A converter using more output binary bits provide for better resolution since it will respond to smaller voltage changes. Resolution is the voltage input unit value that results in a binary output change. An 8-bit converter divides the input reference voltage by 255. The resolution of an 8-bit converter is much better since the voltage resolution is much smaller than a 4-bit converter. Let's examine why an 8-bit converter produces a better result than a 4-bit converter. The 8-bit converter divides the voltage reference by 255. In the example shown, the 15-volt reference is divided by 255. The result is a resolution of 58 millivolts. This means that the converter will produce an additional decimal-weighted binary value for each 58 millivolt unit. It means that there are 255 units of 58 millivolts and 15 volts. If the reference voltage is changed to 10 volts, the resolution is now 39 millivolts. This means that the converter will produce an additional decimal-weighted binary value for each 39 millivolt unit. It means that there are 255 units of 39 millivolts and 10 volts. If the reference voltage is changed to 5 volts, the resolution is now 19 millivolts. This means that the converter will produce an additional decimal-weighted binary value for each 19 millivolt unit. It means that there are 255 units of 19 millivolts and 5 volts. The converter creates a binary output from a scaled input voltage. The input voltage and the resolution of the converter determines the binary output. The 2 steps used to determine the binary output for a specific input voltage are shown here. First, solve for the number of resolution voltage units that are in the input voltage by dividing the input voltage by the resolution of the converter. Next, convert the decimal value into a binary value. This is the decimal-weighted binary value that will be produced by the converter at a specific voltage input. Let's identify the binary output of an 8-bit converter with a 10-volt reference and an input of 7 volts. The resolution is 39 millivolts. It must be determined how many 39 millivolt units are in 7 volts. To do this, 7 is divided by 0.039. The result is 179. This means that the converter will produce a decimal-weighted binary number of 179, which in binary is 10110011. Let's identify the binary output of an 8-bit converter with a 5-volt reference and an input of 3.6 volts. The resolution is 19 millivolts. It must be determined how many 19 millivolt units are in 3.6 volts. To do this, 3.6 is divided by 0.019. The result is 189. This means that the converter will produce a decimal-weighted binary number of 189, which in binary is 10111101. A 16-bit converter divides the voltage reference by 65,535. In this example, the resolution of the 16-bit converter is 76 microvolts. The 16-bit converter changes its binary output for each 76 microvolt change of the input voltage. In this example, the input voltage is 4.1 volts. There are 53,947 units of 76 microvolts. The converter produces a corresponding decimal-weighted binary output of 11010010101111. An analog to digital converter uses a scaled analog input voltage to create a corresponding digital output. The digital output is used for digital control, digital information, and digital display of information. Analog to digital converters, along with digital to analog converters, are vital parts of electrical, automation, and process control systems.